Well, hello friends. Today we are going to work on a memory region attribute called mapStack that I recently read about, and it's this thing that OpenBSD came up with where you can mark a certain memory region as a stack region, and then the kernel can, at various points in time, just go in and double check that your current stack pointer points into a memory region that's designated as a stack region. And if it points to somewhere else, the kernel can just crash you. So it's kind of like I don't know, like an opportunistic security mechanism, basically, because the CPU, the x86 CPU, does not offer any kind of enforcement, like a hardware enforcement of this, but it does seem like a really useful thing. And even if you ignore the security aspect of it, but like obviously you shouldn't completely ignore that, but it's just like generally useful as a bug catching mechanism, because if you have a stack pointer that just runs outside of the stack region, but if it somehow manages to like skip all the way into a valid region, then you might potentially continue running with a stack pointer that's not where it should be. So I think that's a very interesting mechanism, and let's implement it. So I guess the first thing we're going to do is just add a flag for it. So mmap takes an int flags, so we just need to put something here, and we have room. We have lots of room here, so we just call it mapStack. Why not x40? It's just a bit, and these calls, they just forward the flags directly into the kernel. So we just go to sysmmap. Right? Yeah, sysmmap. And we get the flags out here. Then we look at the flags and do various things based on them. So I guess when we allocate a region, we really just want to like set a, like we do here for the shared flag. So we can just do if flags and mapStack set stack true, something like that. And this is the kernel copy of all the flags. I really dislike that we have to duplicate this, but at the moment we do. Okay, and then we'll do the same. So this up here is for anonymous memory mappings, so like not file-backed ones, and then down here comes the file-back stuff. So it's a bit silly that we do the same stuff twice, but I guess that's how this code is laid out at the moment. Stack true, and maybe we can put a fix me here. The rest of this function seems like it could share more code. Right. Okay, now we're going to need, in the region object, which represents a memory region inside of a process, we're going to need the flag is stack, say mstack, and we'll add that flag down here, mstack, and we should also have a set stack. Now, it's important that that we don't provide a way to set this flag after the fact. So it can only ever be set on a new memory mapping by calling mmap. And something that's kind of nice about that is that it will make sure that the memory is always cleared. And this makes me realize that allowing this for file-backed memory mappings is clearly wrong. So we definitely don't care if you have mmap with mapStack and map file, or if you try to share the mapping, I guess. So we should probably enval in those cases. So if it's shared and private, that's enval. So let's say if flags and map stack and flags and map shared, or flags and map. The map file isn't here. If map anonymous is not true, then map stack can only be used with private map anonymous. Cannot be used with shared or file packed mappings. Yeah. And of course, mmap returns a void star. Okay. So if stack and either we have shared or we don't have anonymous. Yeah. Okay. Should we require map private? I guess we can actually. Map private and map shared are a bit strange because they're two separate bits, but they're also exclusive with each other. So just to be on the paranoid safe side here, we can just do map private. So if private is not set, or is anonymous not set, or shared is set. Yeah. Okay. Right. So now we have this thing set up. Now this was just for mmap, but let's also set it up for the kernel's own stack that it creates. So create user space stack. What's it called? Make user space stack for main thread and for secondary thread. So here we create this region, and we can just go ahead and say set stack true. And for the secondary threads, we do the same thing. So let me just say user space stack region set stack true. Okay, so now our stacks should be set up this way. And let's verify this by looking at them in wait, how the hell do we look at these again? I forget. We're going to have to look in the proc file system. Okay, I forget where these things are. So regions, where do we get the regions? PVM, right. So in PVM, we see the readable flag, the writable flag. So we can also show the stack flag. Stack. And I guess we could show the shared flag here, because why not? It's kind of weird that we don't. Let's just have a look at this. And of course, they're not going to show up in the system monitor yet, even though that would be kind of handy right now. So if you look at the terminal, memory maps, then we can see here that we have a stack for the main thread, but we don't see that it's a stack. So we could add something to the access field, perhaps an S. That might be kind of interesting. So let's see where that is. System monitor. No, this is not the thing I'm looking for. Where's access? I guess process memory map, which, right. So here, if object get stack, that would tell us that it's a stack and shared. It's also S. That's annoying. Oh, damn it. What am I supposed to do? H is for shared, or T is for stack? You know, maybe T is for stack this time. I don't know why. It just seemed like we're going to have to make some room here for shared. Because shared memory seems like that one would have been there before if I didn't realize that we didn't already expose the shared bit. So the shared bit was already there. I'm just adding the stack one now. So you got to be T, bro, or S2. Sometimes the only thing that matters is who comes first. So let's looky in the system monitor at the terminal. Geez, I hate that these things resort without moving the selection. I have to fix that at some point. So T is for stack. That's pretty cool. And S here is for shared buffer. Also very cool. So this is terminal's bitmap, backing bitmap that it shares with the Windows server. We can actually see that it's shared. These other things are shared too, but these are read-only. And I don't even know what those are. Maybe the icon, maybe, I don't know. Kind of neat. And you can see that we've also memory mapped this file here, and it's also shared because anyone else who maps the same file will get the same physical memory pages. So it's not a completely immature VM implementation. But anyways, so about this stack thing. So now that we have the T-bit set on this thing, we want to make sure that if we ever veer off, set an invalid stack pointer, then that will be unpopular. So let's make a little Rascal program that will do this. Maybe, oh, we can do this in the Crash program, actually. So we have the Crash program is a program that his only purpose is to provoke a crash in all these different ways. So this is a fun new thing we can add here. Invalid stack pointer. And I guess we can call this the T for the T-bit. Okay. So here, how the heck are we going to do this? Invalid stack pointer is the mode. Maybe we will just make a loop, or we'll do something stupid, or we can make our own stack, I guess. So I'll just say like makeshift stack, and we'll just point the stack pointer straight into that thing. So makeshift ESP is point it straight in the middle, and actually we should maybe we should do this with mmap. Yeah, let's do this with mmap because then we can see better what goes wrong. Okay. Page size, map, anonymous, map private, map stack. Oh, wait. Prot right. Okay. That would be a problem. Okay, and then here we can just do straight into the middle of it. So this should be allowed. So let's see, move. Oh god, how the hell do you do this? I always forget. You move EAX into ESP, and then you say something like, what the hell is the thing you say? Like A should be makeshift ESP. Is that it? Is that it? Invalid escape. Well, I'm sorry. Okay, I think that's maybe it. And then here we'll do a get yield thing. Maybe just get UID. We'll just do some kind of syscall because at the syscall boundary we can do the check. Okay, so let's go into the syscall entry code here and make sure that we check on this thing. So let's see. If process so auto stack region is process region from range. Or how do we get this? Memory manager maybe has this. I forget who has this API. Region from Vatter. Who am I supposed to call for this? This feels like the right API. Region from virtual address. Pass in the process and the virtual address. Validate user read. Yeah, okay, so we can do something like validate user stack. And have a return that the region has to be readable and region, or well, let's just say that it has to be stacked. That's the thing that's interesting. If validate user stack process and regs.esp. I think that's the one we end up using. Then, oh shit, we got a crash. And should we let you handle this, I wonder? Like, I feel like we shouldn't even let you handle this kind of crash. But I'm not really sure. So how do we even use crash normally? Not this way, it seems like. Sig-sev. Send urgent signal to self. Right. Well, maybe we should do it that way for now. Crash. How do we do crash normally? Handle crash. Yeah, we just do this. You know, I think we're going to do this way. Because if you're running around with an invalid stack, then maybe we don't want to invoke the signal handler in that case. Yeah. So we'll just do process, crash, sig-sev, or maybe oh, isn't there a stack fault thing? Sticker. Sure. Damn it, what's the name of it? Where's sig even defined? Signal members. Stack fault. You know, maybe this is where sig stack fault gets to shine. Okay, so we'll say regs EIP, and we probably should not do anything after this point. So this process will die here. So we'll say assert not reached. Because crash, yeah, we'll die. Okay, so if you make a syscall with an invalid stack, we will now crash with stack fault. But this thing should still work because this is a valid stack. We've mapped it with map stack. Survived. Syscall with map stack. And then we'll do an invalid stack. Bad stack. Bad ESP, bad stack, bad ESP. Okay, let's see how this goes. Come on, build faster, bro. This is kind of an interesting mechanism. I guess we could also do this when you get a page fault, because that's also like a synchronous kernel entry. So like we enter the kernel synchronously in, oh, this didn't work out. Where are we? Process crash. Wait, who's crashing? We are crashing too soon here. What process is this even? I don't know. We'll find out. Syscall trap entry. Bad stack. Let's say process bad stack on syscall. Process dump regions. I just want to see what they are. System server has a bad stack, and that's a stack main thread. It's not T-mapped. Wait, why isn't it? Oh wait, dump regions doesn't know about this. This is stack T. And actually, or let's do it this way. I can just cast this to a void star and we'll get it looking like a pointer. Because I can't read decimal pointer address. Come on. What? Oh, dump regions is failing now. Oh, right. Yeah, because I forgot about the format string. Okay, we're having silly problems right now. Okay, so crashing. This is our stack. This should not be our stack. I guess Oh, right, yeah, because syscall takes us from ring 3 to ring 0, so we got to look at ESP if cross ring, because it's a cross ring call. Okay, bad stack. 1, 4 BC. But that's in this one. System server. Why is this? Is it that when we fork, then maybe when we fork and clone all the memory regions, then we don't actually copy them that bit. So we gotta look in region clone. Yeah, this is definitely the issue. So if it's shared, then it should not be a stack. But if it is shared, if it is not shared, or it's readable and not writable, strange. Readable and not writable. Like, we shouldn't have a stack region that's not writable. That doesn't make any sense. So, in this case, we'll say, oops, no stack allowed. Because again, if it's shared or readable, not writable, we don't want to. Maybe we should enforce this at some other level, actually. Like if you get here, assert and stack, and then we'll enforce that elsewhere. But I guess we should make it cal. So cloned region set stack mstack. Okay, and let's see, what do we do? Set stack. When we do this, if map stack, let's see, if flex and map stack and not flex and map read, or not flags. No, this is prot read or not, prot and prot write. Because, yeah, if you try to map a stack that's either not readable or not writable, it's eval. Yeah, that makes sense. Okay, so now we should clone in the forked child process. It will now copy over the stack flag. So we should be able to boot. Cool. And run crash t, then it does survive the syscall with the map stack. But then things go horribly wrong because we have a bad stack on syscall. That much is good. Then in crash, we assert that, crash asserts that interrupts are disabled. Well, we can take care of that. So normally, in all other cases, we've already had interrupts disabled at this point, so we could just do this. I think that would be okay. Or we don't have to cly yet, so we can cly here. Okay, so crash T, and look at that. You made a syscall with a bad stack, and we crashed because of it. How cool is that? Okay, and what does it look like? This is the address that you try to use. How does this normally look? Like, I feel like we should color code this a little bit. Illegal instruction. Yeah, we do this thing. We say like crash. We should do this. Handle crash. I guess we could call handle crash. And we can do cly here. And we'll expose this. We'll expose this somehow, CPU H. I don't know what this should be called. I'll just put it here for now. Struct register dump. Where's register dump defined anyway? It's further down here. All right, well, that's not terribly important. Okay, and then handle crash can now be called from here. So we'll just say handle crash. Regs. Bad stack on syscall entry. Sig stack fault. We'll assert not reached. That could be pretty good. Now, I don't think we want to do this in the scheduler. Like every time that you interrupt the process, you could validate his stack pointer. But I feel like that maybe that's a little too aggressive. But we can certainly do it when the process is synchronously interrupted, either by a page fault or by a syscall that he himself chooses to make a syscall, right? So crash T, and now it looks like this. That's kind of cool. Yeah, awesome. Let's put a dot after the crash description. It's just weird that there's no dot there. Anyway. Okay, so let's do this on Pagefault as well. So handle Pagefault, I guess. Maybe we can do this earlier. Maybe like right up here. Even before we go into the Pagefault handler, we can just say current process virtual address. Okay. Reg ESP. This one is a bit trickier because, like, how do we know if it's cross ring or not? I guess we have to look at the calling code segment. Did we do that somewhere already? I thought maybe there would be somebody who already took care of this. Yeah, right. Something like this. So Q32 ESP to validate. So if the code segment and 3, which is how we find a privilege level, if it is 0, that means we're calling from ring 0, then ESP to validate is reg's ESP. Otherwise, ESP to validate is reg's ESP of cross ring. This could probably be done in a better way, but it is what it is. So ESP validate. It would be nice to actually log the bad pointer as well. Debug. Valid stack pointer. Yeah, we'll say it this way. That'll be okay. This way you can find it. Just so that you have some way to find it. And we'll do the same in the syscall. Syscalls never happen from ring 0, so in that case we know that we're always making a cross ring jump. Also, this stupid name here is annoying. It should be like this. But anyway, don't have to fix that right now. Okay, so will this work? I mean, first thing we gotta do is just do a smoke test to see if our system still boots. It doesn't, right? Bad stack on syscall entry. Well, this should be called bad stack on Pagefault. And if you get a... This should only be done for user processes. Because, yeah, we're not going to validate the kernel stacks at this point. So we'll say if current process is ring 3 and bad stack on Pagefault. So this is a kernel memory address, and ESP here is looking way more valid. So maybe I didn't think this through. What do we say? This is the crash. So crash prints out the right thing. Dump regs. SS is DS. Well, it doesn't seem right. I mean, they're always going to be the same in practice, but that's just a weird typo. If it's ring 0, then we look at this. Otherwise, we look at SS of cross ring. Maybe that's how we'll do it then. Oh, where did I put that code even? Sticker filter. Here we are. Okay. So if it's I guess then we don't even validate unless it's a ring 3 process, in which case we should always be good to go with the cross ring one. I hope. I think I'm getting this right, but maybe I'm not. No, I'm not. Okay. Because now we die because we're in the kernel when we get a page fault. Okay, so we're already in the kernel, we get a page fault, and then at that point we have a kernel stack pointer, which is totally fine. Okay. So let's move this computation. Oh, no, we can't. Okay. If reg cs3 is not 0, what's cs at this point? It's this one. And wait, hold on. Let's look up here. This stack pointer we cannot account for, and it's a kernel address. So it's a kernel stack pointer, and we have to just let it slide. So I guess if the process is in the kernel, then we gotta let it go. So if it's in ring 3 and current process in, do we have something? Is in kernel? It has to not be in the kernel at the moment of calling, so faulted in user space. I guess this is what we can say, really. Okay, so we don't validate the kernel stacks, and then we can know that this is always an ESP of cross-ring. Ugh, all right. Yeah. Isn't this somewhere else? No, I guess not. Okay, so crash T, exiting due to stack fault. Now let's make a variant of that. Valid stack pointer on syscall. And then we'll make one on Pagefault as well. So syscall, maybe the small t can be on Pagefault then. I don't know. Okay, so we can, let's see, we'll have the same kind of setup. We will just make a bad stack this time, and we'll point ESP straight into it, and then we got to trigger a page fault. Maybe the easiest way to do that is to push something. I don't know. Because then it should try to push right into this invalid stack, and I would think that would fail. Oh shit, we don't. Wait, how did I screw this up? Oh, I didn't build that code. No, didn't catch it. All right, so why was I able to push there? Oh, I would have thought that that it would create a 0 fault, because when we mmap a bunch of memory, then we don't actually allocate the physical memory until you try to use it, which is what I thought would happen here. But I don't know. This isn't the type of stuff I do every day, so let's see what the code looks like. I guess mov, ESP, EAX. Oh, okay. EAX. That's the call to get UID, so that's the first this implementation here. And then we mmap our bad stack, call get UID. Oh, that's this one. And then finally, we map a new bad stack. And where's that push? Here, push 0. Why is it letting me do that? That's weird. Why doesn't it Pagefault? Okay, well, let me just see. What happens if we do this? Null header. Make userland. Okay. That also didn't crash. You really shouldn't let me push with this completely screwed up stack pointer. Okay, I'm confused. So what's EAX at this point? Bad ESP, right? What if we do a crash here? So we'll do an undefined opcode, which will provoke a crash. And that should allow us to look at the registers. But am I even running the right code here? I somehow made it. I don't know, like, am I running this code? We're building crash. Well, we don't print I somehow made it. Oh, we get to this one. Oh, shit. Oh, frick, we're not going in here. Because I didn't write Pagefault. Oh, jeez, I'm so silly. Alright, now we should only need one push. See, I was confusing this assert not reached with this one, and I thought we were here, but we were here. Okay, that's more like it. So we got a stack fault, bad stack on Pagefault, and it's null at the moment, because that's what we do here. But we could also point into this valid address space, but it's still not a stack region. Crash T, still stack faults, but now the stack pointer is this 142C800, which is in this range right here that we mapped, does not have a stack bit, and so does not let you Pagefault. Freaking cool. All right, so I think that's the whole feature. It's a big feature, but no, it's not a big feature, but it's a neat feature. So let's see what we've done here. So down here, this is just a crash program where we test the mechanism in 2 different ways. And then we add the map stack define. VM regions now have the stack bit, and when we clone a region, we make sure that we copy over the stack bit. And you know, we could afford to do a little sanity checking there, I think. So let's see. If mstack, let's assert that we didn't get ourselves into a goofy state here. So assert m is readable. It's writable. Assert is not shared. Yeah, that makes sense. Okay, because these things should be enforced elsewhere, so we should never get to the point where we're cloning a stack region that's not readable, not writable, or shared. We can also do assert is VM object is anonymous, let's say. Let's assert that it is anonymous. Otherwise, that would be quite sad. Because you should never have a stack pointer that points into a file. That's just freaking weird. Okay, so here we were just fixing a little typo. Here we were adding, displaying the shared and stack bits in the process manager system monitor application. And here we make Handlecrash callable from the outside world so that we can call it from the syscall trap. And we apply before we call crash, because crash asserts that you are running with interrupts disabled. So that's all good. And then in the Pagefault handler, if you're faulting in user space, which we know because the privilege part of the code selector is 3, then we check if your current process thinks that this is a valid stack pointer. If not, we crash. Okay. Here it's just making Handlecrash callable from the outside. Here is exposing those 2 bits in procfs. So that one we could do separately, actually. And this is process dump regions, and oh, here is mmap. We try to validate a little bit here. Let me add one more comment there. So enval map stack cannot be used. Non-readable, non-writable memory. That would be weird. Okay, and then here when we do a syscall, then user space is the only one who makes syscalls. Like the kernel doesn't need to make syscalls. So we know here that we're calling from user space, and then we just ask the current process, hey, or rather, we ask the memory manager, is this a valid stack pointer for the current process? This could probably be written in a slightly different way, but it's still good. We crash if it's an invalid pointer. Cool. And then here, when we make the user space stacks for threads, then we mark them as stacks. And the process of validating a user stack is just grabbing a region, making sure that there is a region, and then checking the stack bit. Cool. Here's the cloning logic, which this is only used when you fork a process. Then we have to clone all of the memory regions. So that's where we have to do the stack bit copying. Here's the region class, adding the stack field and getter setter. And we're good. Okay, so let's do the kernel stuff first. Syscall, thread, Unix types, libraries, let's see, mman. Here's a land. Okay, so then that leaves only the procfs and system monitor stuff. So we'll commit this. Kernel Implement a map stack for nmap, or implement stack pointer validation. So basic stack pointer validation. New regions can now be marked as stack regions, which is a requirement, which is then dated on syscall and on Pagefault. If a if a thread is caught with its stack pointer not pointing into anything that's not a region with its stack bit set, will crash the whole process with sig stack fault. User space can create custom stacks by must now allocate custom stacks by using nmap with the new map stack flag. This mechanism was first introduced in BSD, and now we have it too. Yay! No. All right, so that's awesome. Then let's just add this as well. So kernel press system monitor, show VM region shared, and stack bits in UI. Expose these to bits flags, region bits through proc bid, and pick them up and make system monitor. No, it doesn't fit. And show them in the system monitor process memory map view. Boom. All right, so that's pretty cool. Forgot to add the possibilities there to the usage string. TT. Rebase. I don't know how many. 4. Okay, and now it should be in that one, right? Yes. Okay, so I think that's going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out while we do some kernel work. And that's fun too. So, stack fault and stack fault. Very awesome. So, shout outs to OpenBSD for coming up with this super neat mechanism. And I'm really happy that we have it now too, because it's a good thing to crash early, crash often if something is wrong with the program. Very, very cool. Yeah. It's just so neat. I'm I was just marveling at how neat this little mechanism is. Okay. So yeah, thanks for hanging out, and I hope you saw something interesting. I will see you next time.